close enough.
Yeah, so you need 2 stacks. Oh well. Any questions? Okay. Let's see. So we have master set 3. Oh, we should talk about test. The first test. April 2nd. Is that next Monday? April 1st. How about test 1A on the 3rd? All right, I got an enthusiastic nod from Kira back there, so. You can think of it, I mean, you put your head down like you were embarrassed, but I just gave you an alibi for this time period, so. The rest of you, don't mention your name. Who knows what trouble you get into. Yes?
The test being open.
No. But I got a bunch of old tests. Oh, by the way, so originally, test 1 covered chapters 2 through 6. And that seemed to be too much material. So I broke the first test into test 1A and 1B. There's still 2 completely separate tests. The 1A and 1B is just a naming convention. So if you're looking at the old test and you see test 1, that's going to cover materials that are on the first 2 tests. If you see test 1A, that's just the first test. Test 1B is just the second test. So I strongly recommend that, well, first off, the master sets are based upon old test problems. So you've got some practice there, but look at the old tests to give you a sense of how long they are. And I do it on lab days because we have the hour and 50 minutes. And, you know, when you're done with test, you may stick around or you may go. You are not a prisoner. Okay. Any other questions? We last left off. Taking you through the facades method. And we spent pretty much all day yesterday doing the force diagrams. And it is a repeat of the videos, as well as I'll have the videos of yesterday posted. So it's important enough that I felt the need to definitely go over it, even though you should have or be watching the videos. However, the rest of it, we should take a look at that. So let's start out with a simple example, of which we'll flash through a whole bunch of these. Box on the ground, being pushed with a 5 Newton force. This has a mass of the box is, we'll make it 3 kilograms. What is the acceleration of the box? So, in a problem like this, you don't have to go through every single step. I'm going to go through all the steps just because it's the process that I'm trying to teach here. So first thing we do is the force diagram. All right, what forces are acting on the box?
Gravitational force.
All right, acting which way on the box?
Acting down on the ground.
All right, so I have weight there, and it comes in pairs, so where's the other part of that?
Up on the ground.
All right, done.
Normal force.
Acting which way on the box?
Up on the box, down on the ground.
Done.
Other.
Yeah, we do have an other. Unlike all the examples yesterday, there is an other here because I didn't mention what really was causing this 5 Newton force. So this is the one, when you're dealing with an other, you don't do the pairs because there is a 5 Newton force pushing that way on something. But 5 newtons, if you want to throw a letter into it, that's fine, as in Q. Because we don't use any English for Q in this course. So other, done.
Friction.
Going which way on the box?
Left.
And on the ground.
Right.
And what about tension? Why is there no tension?
Could be no rope or chain here.
All right. So that is the force diagram, that's the first step. The next step for acceleration is determining the direction of acceleration. So given your life experience, if I push on that box, which way would it accelerate? Yeah. Now, if I pushed on it this way and it suddenly came back at me, then that would probably teach me for pushing on it. But yeah, unless there's some other force involved, it can only accelerate in that direction. So I'm just gonna write a little arrow over here indicating acceleration is in that direction. It is not part of the force diagram. It's just a separate note. So that is the A. Now we set up our coordinate system. This is the CA, the coordinate axes. The strong recommendation is we're going to set up I hat, J hat. Either I hat or J hat is in the direction of acceleration. I'm going to go with the traditional I hat, but if you're feeling saucy, J hat. So I establish my coordinate axes, so there's my I hat, and J hat is perpendicular to that. Up or down, it doesn't matter. Anyone with a preference?
Up.
So we have our coordinate system set up. D is for decompose. As I look at the 4 vectors that are the 4 forces acting on the box, if they are in the I hat or the positive or negative I hat direction or positive negative J hat direction solely, then we don't need to break it up. Is there any vector acting on the box that is not in positive or negative I hat or positive or negative J hat? All right, I got 2 people shaking their head no. We got a third? All right, we got a third, thank you. There's nothing to decompose, so we'll skip over that step. Don't worry, before we're done today, we will decompose some vectors. E, equations of motion. The equations of motion are not the chapter 2, chapter 3 equations. The equations of motion are all based upon Newton's second law of motion. All right, so I'm going to set up my equations. On the left-hand side of the equation, I'm going to have my forces. On the right-hand side, I'm going to have my mass and acceleration. So I'm going to have 2 equations here. I'm going to have an I hat equation and a J hat equation. So every dimension for each object will produce an equation. So When I'm doing my equations, I take all the forces in the positive direction minus the forces in the negative direction. So my I hat equation, what are all the forces in the positive I hat direction?
The 5 newtons.
I'm not gonna write the units because it's just gonna clutter it up, but at the end, my final answer has to have units, but I know what the units of acceleration will be given. I have a mass in kilograms and a force in newtons. I can handle it. All right. Any other positive forces in that I hat, any positive I hat forces?
Friction on the ground.
On the box. All right, so nothing else on the box. You're right, the friction on the ground is in the positive direction, but we're doing the equation of motion for the box, because the ground, that hash marks there indicating that we assume the ground is not moving. All right, minus, what are the forces in the negative direction acting on the box?
Friction on the box.
And that's it, I have two forces in the I hat direction, one's positive, one's negative, equals the mass times, well, my acceleration is in the I hat direction, so times A. My J hat equation. Based on how we came up with this one, what do you think the J hat equation is going to be? Someone take a shot.
0 minus F.
Sorry?
0 minus F.
For J hat?
What was that?
Y minus W.
Yeah, Y minus W. I just,
Never mind.
okay, I was curious how you came up with yours.
Yeah, I was trying to do the opposite, but I forgot that the J hat was going up.
Oh, okay. So my upward one is Y, my downward one is W, and that's equal to? Mass times?
Acceleration.
So I'll put A here? You doing that based upon the way I asked the question?
Yes.
Okay,
You put 0 or nothing,
0. Why is it 0?
because it's not moving up or down.
More specifically, not accelerating up or down. Kelly, you started to raise your hand?
Yeah, so for the I hat direction, if acceleration is going, I might answer one question here when I ask it. If it's going this way, would we not put it in the equation, like it's going negative I hat?
Oh, all right. If I still had I hat going this way, but my acceleration is that way, then here I would have put negative A.
No. So as long as it's on the same,
Yeah, along the same line, yeah.
okay.
Those are the equations of motion right there. In all its glory. Now, ultimately, we're trying to find A, mass we were given, and so the unknowns, mass is the only thing that we were given here, besides the 5. All right, next stop, S, for substitution. Substitution is if I have an equation for any of these right here, is there an independent equation for normal force? And I'll just, spoiler alert, no, there's not. Is there an independent equation for weight? Yes, there is. So let's derive it quickly enough. If I take an object and I drop it, what are all the forces acting on it? Flash back to box falling from yesterday. If I drop it, what are all the forces acting on it?
Gravity, gravitational force.
Okay? That's it. Ignoring air resistance. If I plug into F equals ma, I have one force. I know it's going to accelerate downwards, so I'll just make that the positive direction. And so my force is weight, and that's equal to mass times, well, if it's,
Gravitational force.
that's gravitational force, what's my acceleration for an object in free fall?
Negative 9.8 meters per second squared.
Okay, You caught back some of it, but still a little bit off. Why is it, Jacob?
Little g?
Okay. Little g. All right, so what was wrong with his answer?
Wait, what did he say?
He said negative 9.8, and then there's some pausing, but
Oh.
meters per second squared. What's
There's
wrong with that?
variations in that?
Pardon?
There's variations in that number depending on where you are.
Okay, that's one. There's another issue.
We set J hat down as positive.
Yes, I defined down to be positive,
Oh, I don't remember.
but I was probably standing here blocking you from seeing that.
I couldn't see it anyway, I'm too old.
Yeah, I heard that. All right. So downward I made positive. So whether it's negative 9.8 or 9.8 meters per second squared depends upon one, where you are, and depends upon the positive direction. But this is the formula right here for weight. And so I would take this equation right here, and it becomes y minus mg equals 0, or y is equal to mg. Taking it one step further. But that's the substitution phase. Now there is a formula for friction. I'm going to put it in here. Well, actually, no, not yet. Let's just assume, and I'm just going to throw this in, assume in other words, frictionless. That will definitely not always be the case, but we've got to start somewhere. So in which case we have 5 is equal to my mass times my acceleration. And so my acceleration is 5/3 meters per second squared. Well, I guess officially I haven't really answered the question completely. What would be the correct final answer? And it's not a decimal first fraction problem.
Would it be 5/5 meters per second squared J hat?
Not J hat.
I hat.
I hat. Actually, the original problem over here, it's going to accelerate in that direction.
Right.
So. That would be the final answer. And the second equation we didn't use. If friction became involved, then the second equation becomes crucial. But in this particular case, again, gotta start somewhere. Questions to hear? All right. Box on ready. Indicating the ramp is part of the ground, that all of this is fixed. It's going to give a value here, we'll make that a 37-degree angle, the box right here. And we'll make it let's keep it at a 3-kilogram box. What's the first thing we do?
Separate.
The F for what?
Separate.
What are, oh, as part of doing, okay, I see where you are. Why are we separating, what's the F stand for?
Where's that?
Thank you, all right. You might have said that, but you were talking very softly. And my hearing is, All right, Let's do it. Then tell me a force acting on the box.
Y is going down towards the ramp. Y on the box is going down towards the ramp.
So Y is going that way?
Well,
Oh, that way. What does normal mean in math terms?
wait.
The normal force is called normal force because of math. What does normal mean in math? Okay. Normal means perpendicular. So if you have a line that's normal to a surface, that means it's perpendicular to the surface. So it's called a normal force because it's perpendicular to the surfaces.
Yeah, towards the ramp.
All right, so now we get the direction. Normal force, what's the purpose of a normal force?
From falling through the ground, or any object that you're against.
Yeah. So it's trying to keep the box from going through the ramp, and so it's pushing on the box. So the normal force would be that way on the box.
On the ramp, it'll go down.
Yes. So if there's normal force Y and normal force Y. All right, what another force?
Gravitational force.
Acting which way?
Down.
Why? Didn't mean to stump you with that one.
Isn't that the only direction it goes?
Let's be careful about that. On the smaller object, when you're talking about weight, yes. It basically is pointing downwards because down is defined by the direction the gravitational pull is. Until you change the English language, it has to be acting on the smaller object, down. When you're talking about weight. When you get into the generalized gravitational force, then it can go in pretty much any direction. All right, and, okay.